This is the 7th lesson in our Random Forest series. In this lesson, we will implement missing value imputation using Random Forest. In the previous two videos, we explored how to estimate and impute missing values in both training and test data using the Random Forest proximity matrix. In this video, we'll put everything we've learned into practice by implementing missing value imputation for the Titanic Dataset. Now, let's get started. This code implements missing value imputation for the age feature of the Titanic dataset using a Random Forest proximity matrix. We'll impute missing values in both the training and test sets, and then evaluate the model using the imputed test set. To fully understand this implementation, it helps to be familiar with the proximity matrix concepts covered in these videos. First, we load the Titanic dataset and perform some simple pre-processing. The dataset contains 891 samples and 8 columns. The first column is the target label, and the remaining 7 columns are input features. In the age feature, only 7 to 14 of the 891 samples contain valid values. The remaining 177 entries are missing and are represented as NaN values. This means that nearly 20% of the values in the age feature are missing, which is a fairly high missing value rate. The other features do not contain any missing values. If we look at a few samples from the dataset, we can see that some entries in the age feature contain NaN values. Our goal is to impute these missing values. Next, we separate the dataset into input features X and target labels Y, and then split the data into training and test sets. As you can see, the age feature in the training set contains missing values. The test set also contains missing values. The column index of the age feature is 2. We set the number of trees in the random forest to 50, and the maximum depth of each tree to 5. Now let's begin by replacing the missing age values with the mean age of the corresponding target label. These values serve as the initial estimates for the missing values. First, we find the indices of samples whose age values are NaN in both the training and test sets. Next, we find the indices of training samples whose target label is 0. Throughout this code, variable names beginning with I_ represent index arrays. We then compute the mean age value for each target label. For training samples with target label 0, the mean of the non-missing age values is stored in mean Y0. Likewise, the mean age for samples with target label 1 is stored in mean Y1. In this example, mean Y0 is 31.22 and mean Y1 is 28.0. These values will be used as the initial estimates for the missing age values. For training samples with target label 0, missing age values are replaced with 31.22. For samples with target label 1, missing age values are replaced with 28.0. Let's visualize these initial estimates. All missing age values belonging to target label 0 are initially set to 31.22. while all missing age values belonging to target label 1 are set to 28.00. The age value of the first training sample was originally NaN, and it has been replaced with 28.0. The age value of the third training sample was also missing, and it has been replaced with 31.22. This completes the initial estimation step. Next, we'll refine these initial estimates through an iterative process. To do that, we first define a function that computes the proximity matrix using a trained random forest model. The function takes a trained model and a set of data samples as inputs. First, we determine the leaf node reached by each sample in every tree of the forest. This produces a leaf node assignment table, like the one we saw in the previous video. Each row corresponds to a data sample, and each column corresponds to a tree. In our case, the forest contains 50 trees. Next, we construct a proximity matrix for each tree and add them together. We then set all diagonal elements to 0 and normalize the matrix. There are two common approaches to normalization. One approach is to divide every element by the number of trees. The other approach is column normalization. In this implementation, we use column normalization. An example of the resulting proximity matrix is shown here. In column normalization, each column is normalized independently so that the sum of its values equals 1. Now let's refine these initial estimates over 5 iterations. Ideally, we would continue iterating until the estimates stop changing. However, to keep the implementation simple, we'll perform only 5 iterations. If you wanted to continue until convergence, you could monitor the largest change in any imputed value after each iteration and stop when that change approaches 0. Inside the loop, we first create a random forest classifier and fit it to the training samples. Next, we generate the column normalized proximity matrix. We then create a column vector containing the age feature values from the training samples and multiply it by the proximity matrix. The resulting vector, called uAge, contains the updated estimates for the age feature. We extract the elements corresponding to missing age values from uAge and use them to update the missing age values in the training samples. We repeat this process 5 times. As a result, the missing values in the training set are updated 5 times. Now let's examine the refined estimates. The missing age value in the first training sample was initially estimated as 28.0. And after the iterative updates, it was refined to 36.27. Similarly, that value in the third training sample was initially estimated as 31.22 and was refined to 31.1. Let's visualize the refined estimates. The x-axis represents the indices of training samples that originally contained missing values, and the y-axis represents the estimated age values. The figure on the left shows the initial estimates, while the figure on the right shows the refined estimates. In the left plot, all missing age values for samples with target label 0 are initially estimated as 31.22. while those for samples with target label 1 are initially estimated as 28.0. In the right plot, we can see that the initial estimates have been refined into different values for different samples. Up to this point, we have estimated and imputed missing values in the training samples using the proximity matrix. Next, let's impute the missing values in the test set. Although our test samples contain target labels, we assume that these labels are unknown. We do not use the target labels when computing the initial estimates for missing values in the test samples. Also, since all missing values in the training samples have already been imputed, the training samples no longer contain any missing values. For the test samples, we replace missing age values with the overall mean age computed from the training data. These values serve as the initial estimates for the test samples. Next, we update these initial estimates using the proximity matrix. We combine the training and test data into a single dataset called xdata, and then generate a proximity matrix from this combined dataset. This is the training test proximity matrix that we discussed in the previous video. An example of the leaf node assignment table is shown here. The last row represents the leaf node assignments of the test sample across all trees. An example of the resulting proximity matrix is also shown here. The last row and last column contain the proximity weights associated with the test sample. Next, we create xAge, the age column vector extracted from xdata. We then multiply the xAge vector by the proximity matrix. The resulting vector, uage, contains updated estimates for the age feature. Since uage contains estimates for both training and test samples, we extract only the elements corresponding to the test samples. We then use those values to update the missing age entries in the test samples. As a result, all missing values in the test samples have now been imputed. Unlike the training samples, we cannot iteratively refine the missing values in the test samples. This is because we cannot use the test samples to train the model. Therefore, we compute an initial estimate, perform a single update using the proximity matrix, and stop there. Finally, we feed the test samples into the trained model and predict their target labels. We compare the predicted labels with the known labels and compute the classification accuracy. In this example, the test accuracy is 81.61%. Now let's run the code and see the results. The output looks like this. In this video, we implemented missing value imputation for both training and test samples using the random forest proximity matrix. In the next video, we'll learn how to use the proximity matrix for anomaly detection. Thank you for watching, and I'll see you in the next lesson.